As we saw in the lectures, the Heaviside function is used as a switch, if you like, to turn functions on and off, and thus produce functions that are defined in a piecewise manner. And we want to be able to incorporate these piecewise functions into our differential equations and be able to solve differential equations that feature these piecewise defined functions. So we need to be able to take transforms of products like this we're looking at here, where we have an arbitrary function f, or a function that has a Laplace transform, evaluated at the value t minus a, multiplied by the Heaviside function h, and evaluated at exactly the same argument, t minus a. As before here, t is the independent variable and a is some fixed quantity. And it turns out that knowing the Laplace transform of products in this form is enough to really allow us to take the transform of most of the piecewise defined functions that we will meet in this course. Okay, so this is one of the properties of the transform that's on your table of Laplace transforms, and it can be proved by just resorting back to the original definition of the transform in terms of the integral. So we have the integral of the product of the exponential with the function that we're taking the transform of. Now, we must remember that the Heaviside function in a lot of ways is a very simple thing. It just takes two possible values, either 0 or 1. Everywhere up until the point a, it's equal to 0. Everywhere up until the point t equals a, the Heaviside function is 0. And then for every value of t greater than or equal to a, it is defined to take the value 1. So the effect of that on the integral will be to reduce this integral, which at the moment is taking place over the whole range 0 to infinity, will be to just reduce it to the range from a to infinity. I guess here we have a condition that a step we're talking about is greater than or equal to 0. So the effect of the Heaviside function is just to reduce the integral to 1 like this. So we lose the portion of the integral from 0 up until a, because h is just equal to 0 there, so it just rubs everything out, it makes everything 0. But thereafter, from a on up to infinity, Heaviside function just takes the value 1. So we're just left with these two factors here. Now what we're looking at almost looks like the Laplace transform of the function f. We have an integral over an infinite range. It's not beginning at 0, so we'll have to fix that. And the product of the exponential with the function. So it's kind of looking like the Laplace transform of f at the moment, but not quite. So what we need to do here in order to see exactly how this relates to the transform of f is to use a transformation. So you see here I have the function f evaluated at t minus a and the integral taking place with respect to t. Well, we want to get rid of that shift where the variable of integration is shifted by this constant. So what we want to do is make a substitution, make the substitution that u is equal to t minus a, and that will make du equal to dt, and it will also make, if u is t minus a, then t of course will be u plus a. And when, let's just work out the limits, when t equals infinity, u is also equal to infinity, or rather as t approaches infinity, so does the variable u, and when t is equal to a, the variable u takes the value 0. So that's all the information we need about what happens when we make this change of variable here. So how does that affect the integral? Well, the integral will now be from 0 to infinity, as it's described here, talking about the limits of integration. And our exponential factor changes to e to the minus s of u plus a. Then we have f evaluated at t minus a, but that's just the variable u, and the integration differential there just becomes du. Now this is looking even more like the Laplace transform of f. We have the integral from 0 to infinity of the product of an exponential with the function f. But the exponential factor isn't quite right at the moment. But remember, of course, that a is a fixed quantity, so it's a constant. So we should split the exponential up, like so. Just using the rules for manipulating indices. And then, as I've just said, a is a fixed quantity, so this whole exponential factor here is just a constant. So it can move outside the integral sign. So we have the product of e to the minus sa with this integral here. But consider this integral carefully. This is nothing but the Laplace transform of the function f. The integral from 0 to infinity of e to the minus s u times f of u du. Now we normally quote this definition using the variable t. Here the variable, we see the variable u appearing, but either t or u in this case is just a variable of integration. So what we're looking at is the same thing here. So this is e to the minus sa times the Laplace transform of the function f. Yes, I should put in f of u here, but I mean, whether we call the argument of the function f u or t doesn't